Hello. So this is part five of our Emergent Phenomena Hangout. We're going to be talking about quantum mechanics today. So do you guys want to make a comment first, or how should we do this?
I think the interesting thing is, to me, as I look back upon this course, I think there's been a number of sort of complaints about the way the sort of course was structured, and Helena brought up a couple of decent criticisms. But one of the things that I like is that this course is so modular that you could almost do just any one week individually. Like when this week started, it recapped reductionist approaches. It talked about what emergence meant and how you would actually look at something from an emergent point of view. Talked about energy scales and then gave an example of it. And that's one of the things that I really like about this course, that anyone could walk into this hangout or any hangout for any week just by looking at the one. So even if you didn't do any of the ones before it, don't be concerned. You could just stop into any one week, look at it, and easily and participate in an informed way about the subject.
Right, exactly. I think it's very well structured that way. So speaking of the topics, so they started with wetness, where they're saying that wetness is not described by quantum mechanics, but that it is an emergent phenomena of hydrogen and oxygen. I think that's a rather good point that they made. Um, them talking about that actually made me think about the fact that there's also another emergent phenomena in water, which is that when water freezes, it expands, and water is actually, if I remember correctly, the only liquid that has that property.
Yeah, it's the
And
only one that comes to mind off the top of my head. Yeah, there could be others, but yeah.
there could be others, right? But and if I remember correctly, that has to do with the fact that at the freezing point, which I think is about 4 degrees Celsius, it the water will arrange itself into these hexagonal shapes, which have more space in between them than the free flowing water molecules themselves. And if I remember correctly, that's what causes this expansion.
The interesting thing when you talk about wetness, one of the reasons why I like that example is because everyone knows what wetness is. Like some of these things are sort of hard to define, but if you say you sort of know what it is, because you know the experience of wetness, even if you can't describe it relatively well, you know the experience, you know what someone is talking about. But it's easy to understand how a water molecule doesn't have the property of wetness. It only comes from the interaction of a number of water molecules, because a water molecule only has the properties of those three distinct essentially atoms. But it's collections of water molecules through like van der Waals forces that form a body which has a different set of properties. And I think that's one of the really strong things that comes out of this, is that groups of things, due to the way that they interact, can have very different properties than the things themselves. Now we know this like intuitively because like an airplane can fly, but like the parts of the airplane can't fly. When you put them together, a flying thing emerges from the parts. And it would be very difficult. Like if you took an airplane completely apart to its large scale parts, it would be very difficult to look at that and say, well, that's obviously the structure of a flying thing. Well, imagine if you took all those parts down to their restituent parts and even to their base, essentially structures. Well, you'd no way you'd be able to tell that once assembled, it would be a flying thing. Well, I shouldn't say there's no way, but it would be extremely difficult to actually get that. And I think that's what they're trying to say. Like from a reductionist perspective, when you're going in and looking at it on this bit by bit scale, you can be making a problem like insurmountably hard. And that there's a different way to look at these things if you look at interactions and average behavior.
Oh yeah, absolutely. And speaking of that, that actually reminds me of things like superconductors, where these high temperature yttrium barium superconductors, where you could have a single molecule or assemblage of these yttrium barium atoms, but they themselves don't actually have any form of emergent phenomena such as superconductivity. You have to not only place them in extremely cold temperatures, but then you also have to have a decent bit of these molecules together to create the global effect. And the global effect itself also has a lot of very fascinating properties, such as things like flux spinning and that kind of stuff, the Meissner effect.
Yeah, and I think like even like sort of on a simpler level, I think we can understand like so related to the wet thing. For example, one molecule of water can't conduct electricity at all, right?
Yeah, exactly.
But lots of water molecules can. Not very well because water only ionizes like really tiny amount, like 10 to the negative 14. But it will conduct just relatively poorly.
Yeah, you
But
have to add
one
some
can't conduct
electrolytes.
anything, right? Yeah, right, exactly, which creates the ions, which is what actually
Hmm.
allows electricity to flow. But
Yep.
one molecule won't do anything at all. And the interesting thing is, while most of this course, which is not surprising because it's physicists that essentially are doing it, there's a tremendous amount that comes out in psychology and sociology and just group behavior of people, the things that are very difficult to predict. Like one of the things, for example, that's quite surprising. Like if you look at neighborhoods, neighborhoods are almost always tremendously segregated in some way. It doesn't need to be by race. Sometimes it can be segregated just like by the people who like to play golf versus the people that don't. And so if you look at, for example, a graph of say all the people in an area, and you color the people in red by the people that play baseball, and the people in green by the people that don't play baseball, all of a sudden you'll see these big clusters. And there's a number of people who started studying the underlying effects of, well, what creates these clusters? And if you find, like, for a community which all the white people are and black people are highly separated, does that actually mean that there's a deep element of racism in behind this clustering? And what they found is that it often isn't the case. That clustering can come from very simple rules, with even as small as something like, well, if you just wanted to have two of your nearest neighbors to be similar to you. So if you like to golf, you'd want at least two of your nearest neighbors to be play golf. You have sort of like four immediate nearest neighbors if you don't count diagonals. So if you had two or more, you'd be happy. Even that little tiny rule by itself will cause massive clustering to happen. And it was quite surprising until the people actually did the math and ran the simulations and found out, wow, look, this emerges. But again, like, a cluster can't even happen from one person. Like, it doesn't even make sense to talk about the cluster of a person and even the cluster of two people. Clusters, as a concept itself, let alone the science, only emerges in large groups of people. So again, there's all these fields talking about this, and from a reductionist point of view, it's very difficult. Or from an emergent point of view, when you look at, okay, what are the simple rules of interaction in this group, and what sort of average behavior do we actually have? The behavior comes out like quite simply.
That's really fascinating. I hadn't heard about that research.
Yeah. It's a
And
bunch of it's based on game theory.
right, I mean that makes complete sense that this slight preference in the individuals will create these large aggregate patterns. That really clarifies a lot of things.
Yeah, like you could code that like literally in 5 minutes, right? Set up a
Hmm.
simulation, right? And all you do
Right.
basically is you start off with a population, you make them move randomly, because people are going to move due to jobs and pricing and all that kind of stuff. So there is a small amount of random movement. So all you do is you say when people randomly move, they'll tend to want to move where they'll have at least one or two nearest neighbors. And if they end up to an area where nobody is nearest neighbors to them, like nobody around them plays golf, well, they'll tend to probably want to look for it. And you wouldn't really call like someone who had that like overly biased or like prejudiced or anything, right? If you just wanted to have like, well, I like to play golf, I like to talk about golf, so at least one or two of my neighbors, and all of a sudden you look at it, you'll see these massive big segregation pools of like 80 to 90% coming from that.
Fascinating. So, another interesting example that came up was I don't know if it was brought up or if it was something I just wrote down. It was magnets, where magnets are simply just a piece of soft iron, and if you look at any one individual atom of iron, it has a spin alignment, but that itself won't give rise to a magnet. You have to have a whole grouping of these iron atoms with all their magnetic spins. I think it's spin, right, or is it magnetic
Yeah, that's
pole?
exactly it. Right. Right. You had to
Yeah,
get coherence, right, among them, basically, because
exactly.
otherwise you just get random, right? So you just get a random
Hmm.
patterns of north and south poles, and they're
Right,
just vectors, right? So if you just take a random bunch of vectors and add them up, you'll end up with zero. You just get
right.
essentially noise, right? It's a random walk.
Hmm.
So you had to do something to make them sort of coalesce to line up. That's why you can like magnetize something by just exposing it to another magnet, because you'll sort of get the things to sort of line up, and you can stroke them to make it. It's also why you can demagnetize something by subjecting it to a very
Yep.
severe shock. Just hitting it with something can knock shit out of alignment, right? That's
Right,
an
right.
excellent example because that's something like that only happens again. One thing, just one thing, can't really be a magnet. Well, it sort of is, like as because it would have a pole, but it would
Hmm.
be so small it wouldn't actually function anyway as a magnet. But a large group of them all of a sudden becomes what we physically think of as a magnet, right? And it comes from the same thing. What interaction allows these individual localizations to actually cohere and cohese into a large group, and all of a sudden that thing starts behaving like a magnet. And the study of it comes from let's look at these interactions and actually see, which leads into like the thing when you start talking about anions as these quasi-particles, which sort of emerge from the interaction of other particles. Now, whether or not they are particles or not gets a bit blurry because how do you actually define what a particle is? And there's some
Hmm.
controversy about that, which is why most people refer to them as quasi-particles. But like the definitions of things I never found particularly interesting, like whether or not like Pluto is a planet and all this kind of stuff. Like they're just labels, so I don't really
Right,
I never got really excited about that.
right. It's more about the mechanism, right?
Yeah, like so if you don't want to call Pluto a planet, okay, so you're for whatever, like that doesn't make any difference to me. Like it doesn't make any difference. Like we're still talking about the same thing, right? So when you're talking about an anion, whether or not you want to call it a particle doesn't make any difference to me, right? Like that thing that we're talking about has a specific set of properties. So if you want to say, well, those properties are not what we traditionally call particles, we're going to have to call it something else. Okay, well that's sort of fine, but it's sort of particle-like in a number of sort of aspects. So, but you know, some people really like terms.
Right, right. And just to digress back quickly to more physical things before we jump into the whole particle thing. Another really good example, I think, this one's a bit more esoteric, but is memristors, which you have this assemblage of basically titanium oxide with some vacancies, and that a large voltage will move those vacancies either closer to the pole or away from that pole, and that either increases or decreases the conductivity of a certain material, or specifically the titanium oxide. And just by looking at a piece of titanium oxide, again, you wouldn't expect it to have any sort of memory, let alone, really any interesting properties on its own. But when you have a high amount of them, and then you add a slight bit of doping to it to add those vacancies, then you get this highly interesting effect that this piece of material has a form of memory. That memory is based off of the voltage it's experienced.
Yeah, there's a quite a bit of interesting research done on that in the materials field. It's been a while since I
Mhm.
looked at it because I'm not terribly interested in the application of those materials. But from time to time, people have sent me articles and stuff and asked me questions about it. Some of the more interesting ones are materials that will retain memory that you can sort of program into them at a specific temperature. So imagine you take
Right, like program magnets.
yeah, so you just take a metal, right, and you bend it into a shape of a circle, and you like expose it to a certain temperature, which sets it to that circle. Now, so you relax the temperature, and then you can do anything to that metal, like you can bend it and you can deform it, whatever, and it'll stay that way. But as soon as you expose it back to the temperature, it snaps back into the shape of a circle because it's programmed to be a circle at that temperature. Now, I'm simplifying it quite a bit, but there are metals that actually do behave like that.
Oh yeah, absolutely. Or like I was saying, a program magnet where uh, you have actually encoded a series of magnetic potentials inside of a material, and when these two coded magnets approach each other, you can program them to do different things. So some of them have been programmed to attract at far distances, but then to repel at short distances, and these kind of things work really well for like cabinet locks and that kind of stuff. Other ones will attract in one orientation, but if you spin it 90 degrees, there's no attraction whatsoever. So those can be used for temporary hooks or attachments for carrying cargo and those kind of things. And those particular magnetic properties are a phenomena of the differing magnetic potentials that have been programmed into the face of the magnet. And you could program a single magnetic potential, and that would just simply be a magnet. But when you have a whole cluster of these specially calculated and tuned and aligned magnetic potentials, they can have very novel emergent phenomena that come out.
One of the more say straightforward and practical applications of this way of looking at things is now in materials field, mainly because the amount of information that we now need to manipulate to understand from a reductionist point of view the properties of materials is simply too large. So just a normal alloy will have anywhere between, say, 10 to 20 constituent elements. That alloy has to go through a number of heating and cooling cycles, so it has the temperature and the times that it's been exposed to. And then it also has stresses that undergo through the same, because they can be thermomechanical treatments. And when you look at this, you can end up with a 30 to 50 multivariable function.
Right.
That's just impossible to do anything with, like to come up with a model that could say, put in these 30 to 40 parameters, and here's what the tensile strength will be. It's simply not going to happen. So there's been a revolution in the last probably decade or so. There's been a number of people who are doing it. And what they've done is, okay, well, let's abandon this, because this is the way metals used to be done. Right? Like people would figure out, okay, like this element makes this much strength and this does this, so you can sort of come up with formulas to sort of juggle it, and we sort of know what's going on because you'd investigate what the element does on a fundamental level. Like maybe, for example, it reduces rupture strength. For example, and you'd know the physical process behind this. But when you got that many of them, you can't do it anymore. So what they started to do is just look at large aggregates. So they take all these materials, and you just imagine this big matrix that had all these data points in the matrix, and the data points would encode in the actual elemental composition plus the thermomechanical properties, and then they just look at the actual physical properties that these things map to, and then they're studying to come up with. I think they mainly use like neural networks now to come up with essentially algorithms which
That's
can
what I
predict.
thought.
Yeah,
Yeah.
that's exactly what they do, right? And they
Hmm.
predict behavior. So now they have relatively stable algorithms that you can essentially mix and match. And now the cool thing is, it's not just interpolating. What they've done is they've looked at this and said, well, this kind of suggested that there are alloys that if we take this composition and we process them this way, it looks like, because they use stable things to prevent like extrapolation error, right? So they use training sets and a bunch of other things. So essentially their extrapolations are more like interpolations. So they've been able to come up with like predictive alloys, and they found a number of them. So they're getting really interesting alloys coming out of it. And then again, it's looking at that from a reductionist point of view. It quickly becomes to the point it's impossible to almost do anything with this. The problem is simply too complex, and we're looking at physical interactions between 30 or 50 things. Like if you listen to most people on G Plus talk about science, they have this very weird view that like if you do an experiment, you should only change one variable at a time, and that's the true way to do science. Well, that's the true way to do science if you're in grade 7, right? But
Right.
yeah, in the real world, you can't do that. There's always this massive, big conglomerate mess of stuff that's changing, even the stuff that you're not trying to control, right? There's different amounts of light that fall in, there's temperature, there's wind, there's always dust moving around. All these things are always going on. So there's all these variables sort of mess off to the side. But you're never dealing with systems that are 100% pure. You're never dealing with constant 100% loads or anything, right? So, and I think the interesting thing is as we're moving to more and more complex systems, people are turning to this sort of aggregate, average, statistical approach to information, which is a very different way of looking at, I think, knowledge and information as a whole.
Yeah, that makes sense that they would be using neural networks because there's
Yep.
actually quite a formal proof that a neural network is an arbitrary function approximator. So it can approximate essentially any arbitrary function. So that makes sense that it was able to converge on this kind of stable representation of this highly multidimensional variable space of not only chemical elements but treatment of them and that kind of stuff. That's it's really quite an accomplishment. And so another thing that was mentioned was fractioning, quantum fractioning. So this whole idea that really neutrons and protons are actually an emergent phenomena of quarks, and that the underlying mechanics of quarks are actually what's causing the different properties of neutrons and protons. That it's the collection of charges made that when you sum up the three charges of the constituent quarks, that is what leads to the integer charge of the proton and uh, the neutral charge of the neutron, while the electron does seem to actually be a non-divisible fundamental particle.
An elementary particle, as we know as of right now. Yeah.
Right, right. And so that's one emergent property of quarks. The other interesting emergent property of quarks is actually what's known as color confinement, which is if you attempt to pull away one of the constituent quarks out of a proton or a neutron, what will happen is that this pulling effect, the more energy that you put into pulling away this quark, eventually you get to this point that you've actually added enough energy into the system that you're able to pull out a brand new quark out of the quantum foam. And what this leads to is that you actually never see an isolated quark. You will only ever see quarks that are paired up with other quarks. And yeah, that's a fascinating emergent phenomena of quarks, and they didn't really. It didn't seem like they actually went into it in the video series, but I think something that's definitely worth mentioning.
Yeah, I think essentially what the course is trying to do is get across a couple of fundamental ideas. And one of them is, what does it mean to hold a reductionist point of view? What does it mean to hold an emergent point of view? When do you sort of look at one or the other? And what fields do the other tend to work well? And what they're trying to, and I think they could have went a bit beyond, because like I said, they've mainly focused on some of the on physics, and I think there are many applications beyond that. But I think, like in anything, whenever you get someone presenting material, they're obviously presenting it from sort of their perspective. And even if they bring in other people, they're bringing in other people. Like they're deciding, who to bring in. So I think one of the things is, if you're really interested in a topic, to sort of look for different viewpoints on it. So I think there's game theory approaches to this that would also be kind of interesting. It's not just the harder the physical or the natural sciences that are using this. So I think this course is mainly like someone without a very much of a mathematical background and without even a scientific background could come in and sort of realize there's a different way to sort of look at some of these problems, and maybe it's the case that when we see design, there isn't design, and it could be some very simple rules that are producing these behaviors.
Yeah, do you mind maybe expanding on that game theory example?
Yeah, so there's a whole bunch of mathematical modeling that's done in game theory to try to explain group behavior. Like one of the simple ones is the behavior of standing ovations in crowds, and what causes a standing ovation. And there's a number of people who did some very simple models. And one of the things that they did was that, well, people will tend to do what other people will do. And then they looked at standing ovations, and then you can also do experiments, right, which is sort of what you want to do. And they came up with this idea that the further you are closer to the stage, the more people that can see you. And so what they did was they did this very simple model where they would seed a sort of audience with, because there'd always be like a random element of people who will sort of stand, right? Because like, why do you stand? You stand when whatever standard that you need to have exceeded is sort of close to the standard of the actual performance. And there's some error because like you're interpreting the standard or what all of that is. So if you look at that difference plus some error, that will make you stand. So that's why you would stand. And then you have to look at the interaction between you and the sort of other people.
Right,
So
the
that,
likelihood that
right,
you will stand, that someone else will stand based on you standing.
right. And what happens is they've made a very couple of very simple approximations. So they essentially said that as people move closer to the stage, more people could see them. So whenever one person stood up, there would be a weighted effect because of the number of people that would see him. And then as more people stood up, there would be a weighted effect of them. So if you saw like people start to stand up in succession, so if you saw like a number of people start to stand up really fast, like one after another, you'd have sort of a higher tendency to stand. And so they did this very simple rules, and they made a bunch of simulations, and they thought they had like a relatively solid model. And then they went out and they started actually observing it, and they got really good matches and to physical data. And then they started talking to people, and what they found out was that, well, the people who actually put off productions often know this. So what they do intentionally, like they didn't know the math, they couldn't explain it, but what they knew is that they would seed the audience, and they would seed the audience with people who were like they were just going to stand. It could be their friends, their family members, and they would get them to go towards the front. So when they stood up, because they just noticed when they stood up in the front, it tended to have much higher standing ovations. So
Right.
it's again, it's a very simple thing, like the mathematics of like many people probably wouldn't know how to take that algorithm and write the math out for it, right? To write out that coding for how you would do a simulation on an n-body sort of sample with those kind of interactions. But you don't need to know how to write out the mathematical equations or to code a simulator to just realize, oh yeah, right, like, because the people in the back, like the back row, if they stood up, no one sees them, right? You can't even see the people like two guys over from you. Can see maybe like the guy straight over from you. So only one row essentially is sort of going to see them. But even then, you're really not going to see them because you don't sort of see sideways, right? You mainly sort of see in a cone in front of you. So the people at the back have almost no influence. But as you go down, if you had like everyone in the front row stand up, it would almost set off like a chain reaction. And then they started adding to this model by doing something like, well, wouldn't it be true that if you were with a date and your date stood up, it'd be almost guaranteed for you to stand up? And if you were with a group like a bunch of friends, there'd be a much higher probability. So then they started adding these little like aggregate subgroups to it. And if one person in the subgroup by randomness sort of sent up, there was a really high probability. And then at the end of this model that they had come up with a bunch of little interactions has really strong predictive power in explaining that. And again, like that whole behavior isn't is only a group behavior, right? That's the only that behavior
Right.
doesn't even exist unless there's a group of people.
Yeah, that's interesting because when I was young and I would go to the church, there was this constant pulling down that kneeling, cushion thing,
Yeah,
and I was like, well, I don't want to do it, and then people would look, at me like, why are you not getting down on your knees and
yeah,
kneeling? Exactly that. That's very interesting. Wow. Wow, because that's not the front of the audience, and it's not the back. It's a different type of you know what I'm saying?
yeah.
And
But that same general principle is very easy to understand, right?
oh yes, I understand that part, but the relinquency of the person next to you attitude is kind of different, though, right?
Yep.
Okay, I see what you're saying then. All right.
Yeah, and just to kind of go back to the quarks thing, So in physics, there's really two different. Well, there's multiple different types of quarks, but the whole idea is that quarks either have plus 2/3 or minus 1/3. And how that works out is that so if we want a neutron, then we have 1 plus 2/3 and 2 minus 1/3, and that equals out to be a neutral particle. And if we want a proton, you just have 2 plus 2/3, so that's 4/3, and then a minus 1/3, and that's 3/3, and that's a charge of 1. So it's kind of interesting to think that there are fractional charges, but they're definitely necessary because obviously, I mean, the math works out, and that the again, the emergent phenomena is from these charged particles, you can have a particle that has no charge because the partial charges cancel themselves out, and that's an emergent phenomena of the collection of the specific quarks inside of the particle in question.
Yeah, the other thing to keep in mind too, right, is the only reason that we say quarks have fractional charges is because when the Millikan oil drop experiments, when we were trying to figure out, like, is charge quantized, it could be reduced down to an electron and couldn't be reduced down any further than that. If at that point in time they had found a way to isolate quarks, well, then quarks would have been essentially isolated charges.
Yeah, exactly.
And electrons wouldn't be, you wouldn't have
Right.
fundamental, electrons
Right,
wouldn't be
but
fundamentally
because of
charged.
color, but yeah, because of color capture, you can't isolate them.
Yeah. So I mean, that's just like one of the things that's really weird is that we have this sort of view that the universe exists in arbitrary chunks that we sort of break it up into, right? And one of the things to keep in mind is that all of these things are completely arbitrary. Like base 10 is a completely arbitrary number system. So even when you get numbers out of it that essentially turn out to be whatever, like it's based on an arbitrary number system anyway. And even the things that we look at, what we choose to call like a group or association of things, often it's just an arbitrary choice on our part as well anyway. But like you have to say something in order to start talking about something. You can't talk about distance unless you have something that's going to be some kind of reference point, right? But the
Right.
thing to keep in mind is unless you're looking at purely dimensionless quantities, which don't have units, and there are a number, that's sort of the most fundamental quantities that people talk about are the so-called dimensionless units. But even those dimensionless units
Oh,
have specific bases,
I
right?
actually have an interesting question for you. So there's this one guy who thinks that the fine structure constant is actually a ratio of two speeds, and that is why it's dimensionless. So um, I read this paper. I may not fully understand it, but where it's the ratio of the speed of light outside of the atom and the speed of sound, or the phonons, the speed of the phonons inside of the atom, and that that ratio between the speed of light and the speed of phonons inside of the atom is about 1/37th. So that's a really kind of interesting look into like what is the fundamental meaning of like the fine structure constant.
Yeah, there's a number of ways to look at any of these things when you take the so-called fundamental quantities and you look at ratios of these things, of
Hmm.
combinations of these things, such that the units actually cancel out. That
Right.
means it doesn't actually matter what your unit system is, and therefore they're so-called like fundamental sort of units. And you can sort of play with them and see like what combinations of things produces this, and then are there physical meanings to these so-called fundamental, sort of manipulations. I think it's an interesting
Yeah,
question.
absolutely. And I mean, so and the other interesting thing is that even though something may be dimensionless, it can be dimensionless in a fundamental way that something else is dimensionless. Like it might, so something might be a ratio of speeds and cause it to be dimensionless, but another dimensionless quantity might be a ratio of weights or something like that. Um,
Yeah,
and,
yeah. Like you can take dimensionless ratios of anything, right? Like you can take a
right.
dimensionless ratio of the speed of light to the speed of sound, of the masses of things, like of an electron to a proton. You can do all of these things over and
Yeah.
over again, and you can sort of drift off into this sort of field of numerology. Most of the fine structure, most of the concepts sort of originating around when people start talking about fine structure constants or the like, is when they're looking at ratios of sort of fundamental things like how strong is the electric force relative to how strong is the gravitational force, and what does it actually mean that that kind of ratio is the way that it is, and what makes it that way versus some other way.
Right. I don't know if I was talking about numerology or anything like that. I mean, I was mostly just saying that even though it's you can have these quantities that are dimensionless, they're dimensionless. They have a fundamentally different character, even though they are both kind of lumped into this dimensionless umbrella.
Yeah, right,
And,
exactly. Because like you could take like the age of the universe to the age of the Earth as a dimensionless quantity, right?
yeah, exactly. And yeah, that would be just be numerology. Yeah. And so the one last thing that they did talk about, and then I have a couple other things, but they spoke about the quantum Hall effect as being an emergent phenomenon. Um, maybe just to give, I might butcher it. So Cliff, you're the PhD in physics. You'll have to correct me on this if I'm wrong. But if I remember correctly, the Hall effect is that given a material with a current charge through it, pass through it, there's actually a current that is also generated across the direction of the charge. So say you have a rectangular plate and then you pass a charge through it long ways. There's also an equivalent charge if you measure it across the short part of, or the short side of the, or the distance of that material. And so it seems that the quantum Hall effect is a quantum version of this Hall effect on charged particles.
Yeah, the main thing and the reason why it comes out, and the specific thing, is that the quantum Hall effect is a two-dimensional system. The reason why that's important is because when you look at, okay, so the two main classical statistical ways are Bose-Einstein condensate statistics and the other statistics,
Fermi Dirac.
right, for statistics. So because those are three-dimensional groups, and in three-dimensional groups, you'll only end up with essentially two solutions. One where there's essentially no change, and one where the change is -1. So if you have a particle go through a change and then go through the exact opposite change, it should end up to where it actually was in the beginning, due to a property of
Right, and
group symmetry, right?
that's exactly, yeah, time reversal symmetry, right?
Right, so that's why you only get two solutions. You get the negative, so you get -1 times -1 goes to 0, goes to 1, or you just get essentially 1 times 1 goes to 1. So those are two possible solutions in the three-dimensional group, because three-dimensional groups can reduce to point transforms. But
Oh, and so
two-dimensional,
you're talking about abelian groups, right?
right, but two-dimensionals can't, right? So
Hmm.
because they can't be reduced to point transforms, you get all these fractional solutions. And the fractional solutions are essentially, they govern the actual spin characteristics of the systems. So you end up with these properties with fractional properties. And that's where the anions come into it. Because essentially you have groups of particles, and the groups, or interactions, whatever you want to call them. So that group of particles could be considered a particle itself. But it's not really isolated. Like when people think of particles, they think of like billiard balls, right? Like something you could grab in your hand and sort of throw and bop somebody in the head with it. That's a particle. So it seems weird to think on like
Yeah,
three sort of balls being
yeah,
a particle, right?
right,
But
connected by like springs or something like
or
that.
whatever. But like they're not really like, so if I ask you to think of a water molecule, right? Like you'll think of one thing. And you'll think of one thing that's a collection of three things, but it's really like sort of one thing because the three things are like bounded together by like bonds or whatever it is, right? But these groups are not really bonded in that way. They're really a group just simply because of the way they're sort of interacting with each other. Like in the same way, for example, you could think maybe of, you have sort of like a relay race where you have like three people sort of running around and handing off a baton. Now, you wouldn't really think of those three people as like a person, but you can sort of think of them as a group because of the way they're sort of interacting in time or space. And if you think of them that way, you can sort of think about those three people in time or space can sort of be thought like a person with weird properties. And that's one of the things they're talking about. So when they talk about anions and they're talking about quasi-particles, they're saying like, well, let's just think about this as a particle with a very specific kind of weird viewpoint, because it really isn't a thing, but it has a time and space sort of behavior, and that's where they get into these fractional properties. But it essentially comes
Right,
back
and
because
and,
it's a
and those are quite distinct from things like virtual particles, which are more of like a bookkeeping mechanism.
yeah.
Uh,
There's a bit about what they are and what they aren't, and vertical particles can essentially exist as real particles depending on what the interaction is, and they can have real physical effect, like they cause
right.
radiation from black holes and a bunch of other things.
Exactly.
But yeah, so it's an interesting thing, and that leads into the talk on quantum computing, because these things um, can hold information at a much denser form than normal traditional computers. The
Mhm.
interesting thing, which I almost sort of thought that they were going to talk about, but they never did, like all this math. So I think they talk a bit about knots, right? So all this math goes back to, of course, Kelvin. You know, the chemist, Lord Kelvin. They all had cool names back then. Like no one gets these names now, right? But anyway,
Yeah, yeah.
Lord Kelvin. Okay, so him and his buddy, they do this experiment. You know, when you ever see someone smoke and they can get really good and they can blow it like a smoke ring. And so they start observing this, and Kelvin comes up with this theory for why these smoke rings form and how they're stable. And he has a bunch of theorems, and one of them is that the frictional interface of the fluid that is propagating in is the thing that breaks up the ring. If there was no frictional interface, the ring would essentially propagate forever into fluid because it's self-stable because it in this sort of whirling sort of format.
Right.
And he has this weird idea because the ether was really big back then, right? We were all surrounded
Hmm.
by this ether, and that's what everything.
Right.
Because you needed a medium for stuff to go through. So light got here, it had to go through the ether because you couldn't propagate through a void. So he has this idea that okay, so if these sort of whirling whorls or whatever they were, if they would propagate forever in a sort of frictionless interface, and the ether is frictionless interface, maybe the fundamental constituents of matter itself, like hydrogen and all these things, are just arrangements of these sort of whirls. And this was a prevailing theory for about 10 or so years. And then it gets overturned for a bunch of other reasons. But his buddy makes it sort of, and I can't remember his buddy's name, which is horrible, probably because he didn't have a cool name like Lord Kelvin. Spends like the rest of his life, 30 or 40 years, working on the sort of mathematics for these worlds and the knots and the orientations of them. And it it's really cool mathematically, but the physics is sort of blast off forever. But now all of a sudden there's this resurgence in it, and it's the exact same math that they were doing back in those times, but it had a completely different thing. Like they were looking at macroscopic sort of properties and then mapping it to a fundamental level. But it's the same thing now to come out in quantum computing. And the thing that always amazes me, like when people start talking about science, I think one of the wondrous things is, can you ever imagine that there's this really strong connection between somebody blowing a smoke ring and this quantum computer, but
Oh,
fundamentally the
yeah.
mathematics are the same. Like that's such a wonderful thing.
Right. I was actually just going to say that you have these kind of fractal systems that have self-similarity at multiple levels, and I think that that also has something to do with emergence, where we talk about length scales and that kind of stuff.
Yeah, there was a really nice bit about that. The only thing that I didn't like this week, and maybe it's just me, I probably should revisit it. I don't like the way that they talk about like there's this competition between entropy and energy, and I never really understood why people talk about that. But it could be just a way that, because sometimes like you learn a particular concept and it's very clear to you the way that you learn it. So you frame everything in that point of view. And I remember I had like an excellent instructor in thermodynamics. And that thing that they're talking about is normally referred to as the Gibbs free energy. And you can write a function for Gibbs free energy, which holds an enthalpy term and an entropy term.
Right, exactly.
Right. And so most people talk about this in sort of a competition, but what this guy does is say, just like, look, what's this all based on? So we sort of know for spontaneous processes, the entropy of the universe itself should increase in a spontaneous process. From our fundamental laws of thermodynamics, most of the time there's a high probability. So he just writes down this expression. So he goes like the entropy of the universe is the entropy change of a system plus the entropy change of its surroundings. He takes those two things, shows how one of them, well, it's just the entropy, that's what you end up with, and the other one is essentially going to be the heat exchange. So he writes the whole thing down, multiplies it all by basically temperature. The right-hand side is the expression that everyone is used to seeing. Basically, it's the enthalpy minus the entropy times the temperature. And the other one is just sort of the entropy of the universe times T. And he said, well, let's just call this like an energy. So we'll just put a label on and we'll call it G. And he says, now look at it. Like, we know this thing is going to be positive for spontaneous process, which means for spontaneous process, the other side has to be negative. Lo and behold, that's what we actually see. When the difference between enthalpy and entropy times the temperature is negative, the process is spontaneous. But for me, it always made perfect sense because it traces right back to the fundamental laws of thermodynamics, which says the entropy of the universe has to increase. That's going to be positive, again, due to Boltzmann most of the time. And that's the way I've always thought about it, as a competition between entropies, not in terms of energy and entropy, which never made any sense to me when people talked about it.
That's really insightful.
But again, that's just because, like, if I had to take a chemistry course, maybe instead of physics, I was doing
Yeah.
because there was two tracks, right? And I always avoided the chemistry ones, and I always did the physics ones because they were
That,
more
hey,
math
me
and less
too,
theory.
me too. So, this wasn't mentioned, but this was something that I think is another good example, which is the Casimir effect, where you can have two plates that are placed very close together, and what those plates do is that they act essentially as a low band or a low pass filter on the quantum fluctuations that are allowed to occupy the space between those plates. So that means that or no, sorry, it's a high pass filter, not a low pass filter. But so where the high frequency perturbations can exist in between these two plates, but the much lower frequencies simply cannot. And so what happens is that because of this high pass filtering, you have a pressure that is exerted from the outside inward because these plates are restricting the possible perturbation states that can exist in between them, and thus have a lower pressure than the summation of all of the perturbations on the outside of the two plates. And so this can only exist with this very specific arrangement of these two plates being close together, but also with the different frequencies of these perturbations. So if we only had one frequency of perturbations and it fit inside of the plates, then the Casimir effect wouldn't occur. You have to have these multiple frequencies of these perturbations.
Yeah, the interesting thing about that, and it's like so much of science, right? Like, he was looking for something completely different. He was looking for Van der Waals
Right.
forces, right? When
Yeah.
he first started studying this. And then he finds, because a lot of people think, I don't know where they get this idea from, that quantum mechanics only does weird things on small levels. Like, there's no actual macroscopic
Yeah.
effects of quantum mechanics, which is weird, which isn't true. But, like, that's a macroscopic effect. The actual pressure between
Well,
these
I mean,
plates. Yeah,
there's some people that say they go one step further and say that quantum mechanical phenomena, and I'm not endorsing this point of view. I'm just saying that some people hold it that it goes all the way up to our conscious level, our macro level, and there'll be some people that will claim that if nobody was observing the moon, that it would revert back to its primitive wave function rather than be a concrete object. But I think that's more of a bastardization of
Yeah,
the
like
science. And
I think
yeah,
the
yeah.
unfortunate thing is like when you're introducing a topic to someone, right? Like, okay, so say you want a kid and you want to introduce him to a concept of numbers, right? So you get him to the idea that numbers are sort of placeholders for amounts of things. That takes a
Mhm.
while, but sort of you can get an idea, like, because a kid can sort of realize, okay, this is one thing, this is two things, and adding is easy because you can sort of look at two things. Subtraction is kind of hard. So the way you do subtraction is you do it sort of in reverse. So 3 subtract 2 means what do you add to 2 to get 3? Because adding is intuitive. But things like 2 minus 3 doesn't make any sense, right? Because you can't do that. Like if you have 2 apples, I can't take 3 from you. But it takes you a while to realize, well, I guess you could, right? Maybe I could say, like, that would mean you would owe me an apple. I would take the 2, and you would owe me 1. So let's just represent a way of how would we represent this, and then you come up with negative numbers. Um, so a lot of these people read, maybe I never do a quantum mechanics course, but they maybe read something, and they read something on the observer effect. So people will read something like, okay, there's this crazy thing with a double slit experiment, where there's electrons are fired through 2 slits, and if you don't look at the electrons, there's an interference pattern. But if you look at the electrons, the
Yes.
interference pattern is destroyed. It's not looking at the electrons that destroys it.
Right. It's actually
It's the actual
firing
entanglement with other
particle.
particles, right?
Yeah,
But of
exactly.
course, you can't introduce someone to the concept of entanglement. They don't have the mathematical framework to
Okay.
grasp.
Right, right. And I mean, if I remember correctly, I think I was quoting I don't think it was Neil deGrasse Tyson, but it was someone, and you know, he was obviously just throwing this idea out as more of a flight of fancy than a serious scientific conception or anything.
Yeah, because I mean, I've said the same thing. I mean, like I said, you have to introduce things to people. In the same way, for example, you tell people, like, you can't square root a negative number. It doesn't make any sense. When you're first talking about square roots and sort of rationals and exponents, you have to give people a sort of idea, and they intuitively know, okay, the square root of 9 is 3, because 3 times 3 is 9. What do you multiply to get minus 5? I don't even know what you multiply to get 5, let alone minus 5. But then as you
Right.
move sort of beyond this, you can get a mathematical framework. If you move beyond a sort of general introduction, you start talking about, like, the actual interactions, the entanglements between particles, you realize that just like you can actually subject them to an entanglement, which will destroy the interference pattern, right after that you can subject them to an opposite entanglement, which removes that and which causes the interference pattern again. So it's looking at it twice in the right way, and the interference pattern comes back. So it's not looking at it, it's the way that it interacts with other objects in the world. So it
Right.
has nothing to do with looking at it. But I mean, it's again,
The
it's
wave.
you had to give
The
people a
wave,
hand.
though.
Yep. Go ahead, Jim.
Because I'm a layman at this, but is that because the double slit in the entanglement thing? Is that the same as the wave energy format, or is this strictly on the photon level?
Well, the double slit experiment can be done essentially with anything. It doesn't need to be done with photons. It can actually be done with
Right.
particles. There's been some recent experiments done showing double slit behavior with macroscopic particles, particles big enough that you can actually see. And because of this, there's a reemergence of interest into Bohemian-based statistical approaches to quantum mechanics, which is generally not. You'll never ever do anything on Bohemian statistics, even if you do a full degree in physics, unless you specialize in quantum mechanics, mainly because the math is too intractable. The math that you need to do the sort of Copenhagen version, which is what most people sort of think about or what most people are introduced to, you can do essentially, like if you do AP Calc in high school, you would be prepared to do that. It's not sort of that much more difficult. But the Bohemian statistics is a two-track problem. You have to go a bit further to do it. And to this date, it has never been shown that it's any better at explaining what happens. So why would you use a more complicated
Oh,
approach?
you're saying Bohemian. That confused me a second. You meant Bohemian.
Yeah. So, but the interesting thing is they've actually shown the experiments. It's very easy to show on a macroscopic level. So it's very easy to think about. So imagine, for example,
Right. Bohmian statistics is
right,
very intuitive. Uh,
right.
yeah.
So just think of a wave like on a pond, right? Okay, so you just got a wave on a pond. Now imagine I do the double slit experiment and I just slam two slits down sort of in the middle of the pond. It's very easy for you to think about the sort of wave going up, hitting the slits, putting a diffraction pattern around the slits, and it will produce an
Okay. Yeah.
interference effect,
Yeah.
right?
Exactly.
Very easy, right? Because you think about waves. So a number of people have done experiments like, well, if you think about that, you could imagine sort of objects like little pieces of cork that are floating on top of the wave. And you could look how these individual particles, as they're being tracked by the wave, will move and they will produce an interference pattern because the distribution of the particles is being
Ooh,
undermined by the wave. That's that
okay.
approach to quantum mechanics.
Thank you. Fine.
So, here's kind of an interesting thought experiment, and I'd like to get your opinion on it, Cliff, where it may be possible to actually theoretically transmit a single bit of information faster than the speed of light, and how how that's done is that, so imagine you have an infinite quantum well, where there's a series of particle, or not series, just a whole bunch of particles bouncing around inside of this infinite quantum well. Now let's imagine that one of the sides, it actually isn't entirely infinite. It does leak. It does allow some quantum tunneling through it. So if we wanted to send this one bit of information, what we could do is at time zero, to measure how many of these particles leaked out the leaky side, and to take that measurement. And at time one is when the information is going to be sent. And to signal a one, we would just keep the wall on the other side up, but to signal a zero, we would actually take the wall down. And so what would happen is, if we took the wall down completely on the non-leaky side, then the leaky side would actually have half as few particles tunnel through it. While if we kept the wall up, then we'd have exactly the same amount of particles tunnel through as we did at time zero. So, kind of interesting thought experiment to be able to transfer a single bit of energy, or a single bit of information faster than the speed of light. But not very useful though.
Yeah, you can look at approximations to an infinite well, right? So
hmm
potentials don't need to be infinite for probabilities to essentially approach zero. So you
Right.
could look at it from that point of view.
Yeah. Yeah. Absolutely. Um, Well, so I here's my last point, and then I'll be all out. So the last thing that this whole talk made me think about was electron shielding. So where you can have a negatively charged particle, but if it's surrounded by positively charged particles, the net charge when viewed from quote unquote afar will appear to be either neutral or positive, because all of these positively charged particles that are surrounding this negatively charged particle are kind of shielding the that negative charge. And again, this is an emergent phenomenon because it requires multiple particles interacting in a special configuration. Um,
Yeah, I think one of the interesting things about that, and it's one of the things that some people don't grasp right away, but there's absolutely no difference from the point of view of our understanding of physics about the behavior of a space which is subject to no electric field as the behavior of a space which is subject to the superposition of two exactly opposite electric fields, one positive or one negative. There's nothing in any of the physics that we know that would say there's anything different about those two fields, because in both of them, the electric field is essentially zero. And that comes out of essentially the Newton's F equals ma, which is such a trivial formula, but people very rarely see the power of it because they don't understand that left-hand side F thing is sum of. and it's a vector sum. And vectors have very weird sums because they can sum to zero even when there's a lot of them, which intuitively you don't think. You don't think like, well, I could sum up a lot of apples and end up with no apples. And most people don't really talk about vector quantities, but they're easy to
Right,
understand if
because
you think about debt,
yeah,
right?
it's got a magnitude and a direction.
Right. So you can think about, well, you could easily sum up a money and have nothing because you could have an income and you could have debt, so the sum would be zero. And people say, okay, well, I understand what you mean now. But the interesting thing, and which Newton proposed, which is now fundamental to all physics, is there's no difference between a system which has like a real zero, as in nothing is going on, between a system that has two completely opposite fields of any given nature that's put on it. So there's no difference whatsoever between a system which has an electron shielded by positive charges between another system which doesn't have that electron at all and just has reduced positive charges. They're distinguishable. There's no way that they can be separated from the outside. Once you get out,
Huh.
if you're inside the system, they're different, right? Because if they're inside the system, if
Right.
they're inside the positive shell, you can actually experience it because it's not symmetric from the inside. It will be from the outside if you're far enough away. Essentially, if you calculate the electric field, you'll have a small non-zero element, which is due to the relationship of your distance to the distance between the shield and the subcharge on the inside. So at very high distances, that goes to zero. But that's a very interesting concept, and it's interesting to think about. Like it goes back to that experiment where Einstein, who was such a brilliant man that he could think about questions and get tremendously powerful interpretations out of them, and he was thinking about acceleration and the sort of elevator paradox, which seems a bit weird. If you're inside an elevator, sort of that you can't see, imagine the elevator's like really, really big, and there's no way to know that you're inside an elevator. Intuitively, there's no experiment that you could do to show that you're in an elevator as being opposed to being in a higher gravitational well. There's
Right.
nothing. The equations are exactly the same. And Einstein started thinking about this and realizing, well, if you can't do an experiment to show, if the physics is exactly the same, well then how can you say that it's actually one thing and not the other? You can't really say it's gravitation and not acceleration if there's no way empirically to tell. I mean, science is all about the reason that we know it's X is because empirically we can show X. So he says, well, maybe it's not a force. Maybe it's an acceleration. Maybe all we're actually seeing is the effect of acceleration perturbations, which is weird because now you're not even talking about gravitation as a force. You're talking about gravitation as a distortion in space-time, which is really weird because it's not a force then. So he rewrites all of this stuff in terms of distortions of space-time. So gravity is not really a force as much as it's how matter warps space. And lo and behold, it all works, which is one of the reasons why many people think we'll never unify gravity with electromagnetism or anything else, because there are forces and
Yeah,
that's not.
exactly. Because you have those problems where gravitons are just packets of negative momentum, and that really doesn't make sense to me at all.
Well, yeah, if you can go back to thinking about it from another paradigm, right? Because essentially the way that we think about forces is through interactions of gauge particles, right?
Hmm.
So photons are a gauge particle for the electromagnetic field. So you can think about a gravitational field having gravitons, which would be their gauge particle, but that's fundamentally different than general theory of relativity. But I mean, we don't know general relativity is right, or classical views on space-time is right. In fact, we know probably that it's not. Because it leaves big holes in our understanding, and there are things we can't explain in celestial and both macroscopic, microscopic objects. But from what we have right now, there's nothing that sort of does any better than it. So,
Yeah, absolutely. And the other thing, as you were speaking, that I thought of too was the charge distribution of protons and neutrons. How actually a neutron, pretty close to its core, is actually positive charge, but that it has a negatively charged skin, and that both of those forces, when you integrate over them, equal out. While a proton has a very strong positive force on the inside, and that it kind of slowly slopes off, but it still remains positive throughout.
right, and
And
unless you're inside the thing, you can't see that, right?
yeah, exactly. And so, and the other thing is also this was something that I kind of had predicted, it was kind of intuitive, but I was surprised that I was actually right, was that the nuclear radius will actually change based on how much a valence shell is built up. So where when the valence shells are completely built up, if I remember correctly, the radius actually drops. And then as soon as you have the first electron in the valence shell, all of a sudden the radius expands. But when you add more electrons and protons, obviously, to the core, the radius of the atom kind of starts to shrink again, shrink, 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 shrink. And that overall, actually, the radiuses of the atoms doesn't change all that much. It just kind of wildly fluctuates in this band, depending on how much the of the outer shell is filled. So I found that really interesting. Have you seen that graph?
No, I didn't think so. I'm going to look it up now. It sounds interesting.
Yeah. Let me see. Where is it? There's like a line graph. Ah, here it is. Yeah, so where the peaks, yeah, have a single electron in the valence shell, but the troughs have all the valence shells completely filled. So lithium, sodium, and potassium are actually have the largest atomic radii, while helium, neon, argon, and krypton have the smallest atomic radii. And the fascinating thing is that uh, sodium actually has a larger atomic radii than argon, even though argon has a larger atomic number. It's kind of really interesting to think about. And that just has to do with the charge balance, because that makes sense, because you have this when the valence shells aren't completely filled, that you would expect the electrons to kind of be flying further out, I guess, or maybe that's just my intuition. Did you find an appropriate picture, or here I got a link right here, Cliff, for you.
Cool.
Yeah. I can't quite screen share. I should have opened this up in Google Chrome, but I do not. But
I can screen share it for you if you want.
sure, go right ahead, please.
Okay.
But yeah, isn't that cool, Cliff? Cliff?
Oh, I'm looking at it now, yeah.
Oh yeah. It's kind of interesting that, like I said, that the radius doesn't actually correlate with the atomic number. It correlates more with how many valence electrons are filled, and it does kind of gradually go up with the atomic number, but the amount of shells, the valence shells that are filled is much more important. Yeah, here you go. I'll present you. Yeah, there you go. So you have these peaks and troughs.
Oh, darn it. Darn it. Sorry.
Infinite blast off.
I gotta turn it off for a second.
No, just go over to the other tab. You're fine.
Oh, okay, you're right. Thank you.
Yeah.
There we go.
Ooh, there you go. Actually, just pull that. You could probably just pull that tab out and have it focus on that, maybe. Don't worry about it. But that's probably enough for the audience, so that they can see that that first purple dot is hydrogen, and then helium is smaller than hydrogen, which is interesting to think about. That you'd think that helium would be have a bigger atomic radius than hydrogen, but it doesn't. And then it goes to lithium there as the third one. So lithium is much larger than helium and hydrogen as an atomic radius. But then you go further down, and those p block, those green dots, actually eventually becomes smaller than hydrogen. So, you have these atomic numbers at around 10, but the atomic radius is smaller than an atom of something atomic number 1. So,
Hmm.
yeah, fascinating how physics works. Even though this is, I would consider this, I'm guessing this more of a chemistry thing. But yeah, this is an emergent phenomena of the charge balances between the outer valence electrons and the inner core nucleus. And again, it's an emergent phenomenon because it's a phenomenon based on collective effects. Anyway, got any more talking points, or do you think it's about done?
Yeah, I think next week will be kind of interesting.
Yeah, I think so too.
I think I'm gonna fire right into that as soon as we're over with this because I'm really interested to see what they had to say about consciousness.
Yeah, definitely. Sounds good. All right. Well, thank you so much, Jim. Thank you so much, Cliff. This was really enjoyable. So, see you next week.
Cool. Thanks.